So this is great stuff. We've got example 1. We're going to be looking at the graph of f of x. You can see y equals f of x. This is the graph. Now f of x, remember, is the same thing as f of t, so when we replace x with t, it really means the same exact thing. It's just that we use a different variable so that we don't get confused when we're dealing with an integral function. Okay, so f of x, though, is the rate at which the snowfall is changing over a period of time. So what we have down here is the horizontal axis is our time in hours, okay, x or t, whatever you want to call it, in hours, and then over here, up here we have f of x, and that's in inches per hour. So the rate at which the snow, it really should say snow level, is changing over a period of time, so the level of snow. Because if you notice here, when x is equal to 1, we have 1, 2, 3, 4, 5, and so forth, 7 and 8. So when x is equal to 1, snow is falling at a rate of 3 inches per hour, because we have the coordinates here, 1, 3, meaning 3 inches per hour. So obviously it's snowing at a greater rate than it was at t equals 0. Okay, and at t equals 2, it's snowing at the same rate at 3 inches per hour. But then down here at t equals 3 hours, at the 3-hour mark, it stops snowing, but it's cold enough to where the snow is not melting either, so the snow level is not changing there. And then over here at the coordinates 4, negative 4, we see that the snow is actually melting at the 4-hour mark. The snow is melting at a rate of 4 inches per hour. Okay, so that's how we read the graph in terms of a rate of change of the level at which the snow is changing. Okay, so the snow level has a rate of change. Okay, and then we're going to complete the chart down here. Okay, we already know that capital F of x is the integral from 0 to x. Okay, and actually, let's do this first. Let's figure out what the areas of each of these regions are. Okay, so these key areas here, let's just figure out what those are, then we can just easily fill out our chart. Okay, so here 0 to 1 there, and so this box, and it's kind of stretched out in the x direction, has an area of 1 by 1. Okay, so this is 1, 2, 3, and so forth. Okay, so anyway, area of 1 there, and then we have over 1 and up 2, so 2 divided by 2 is 1, so that box right there has an area of 1. And then here, this box has an area of 1, 2, 3, okay, and this one, just like the other one, has an area of 2, remember 1 plus 1 over here, okay, and then down here, be careful here, you have 1, 2, 3, 4, 4 times 1 is 4, and divide that by, oh, I messed up. Did that again? Oh, what the heck? Why is that up 3 and over 1? That's 3. Oh, okay. Yeah, that. Sorry, I did make a mistake there, so I caught myself. This, if that went down there, it would be 3 halves. But this is actually 3 halves, so you may have caught that. Up 3 and over 1 is 3 divided by 2. So this is a 1 there and a 1 there. So this whole thing is 2 because it's a trapezoid instead of a triangle. So I didn't catch that at first, but I did now. Okay, so then we have 1 by 4, and 4 times 1 is 4, and divide that by 2, and you get 2. Same with this one over here. Okay, sorry for that little hiccup. Over here we have over 1 and up 1, so we have a 1/2 there. And then this one, we're just going to assume this is the halfway point, and so that was a 1/4 there, so over a half and up 1, half of a half is a 1/4, and this area here is 1 over 4 as well. And then this area here would be 1 by 1, so the area is 1. Now we can go ahead and start filling out the chart. Okay, let's scoot that up right to there. Remember that capital F of x represents the integral from 0 to x. So when x is equal to 0, we have the integral from 0 to 0, and we know that that is 0. When the upper and lower limits are the same, the integral has a value of 0. Now, the integral from 0 to 1 then, when x is equal to 1, the integral from 0 to 1 is all the area underneath this, this curve here from 0 to 1, and we already determined that that was 2. The integral, when x is 2, the integral from 0 to 2 would be 3 plus 2, that's 5. And then we have 5 plus 3 halves. 5 plus 3 halves. I'm going to just leave it like that because I don't have any other room to simplify that. Okay, but now we're probably going to need that though. So 10 halves and 3 halves is 13 halves. So I'll put that right underneath there, 13 halves. Then we need to know, we need to remember that the integral, so when x is equal to 4, we have the area above the curve, which is 13 halves, minus the area below the curve, which is 2. So we have 13 halves minus 2. Okay? And then we have minus 2 more when x is equal to 5. So we have 13 halves minus 2 more, which is minus 4. Okay? So then, when we go all the way to 6, when x is equal to 6, we have the integral from 0 to 6, and so it's all the area above, minus this area here, and then plus that area there. So 13 halves plus 1 half is 14 halves, so that's 7. And 7 minus 4 is 3. Okay? So the integral from 0 to 6 would be 3, because again, and I'll write that right underneath there, that would be 13 halves minus 4 plus 1 half. That's how we found the area underneath, well, that's how we found the net area. In other words, the integral from 0 to 6. Okay? And then 6 1/2, we have all that. We have that 3 plus 1/4. 3 plus 1/4 for the integral from 0 to 6 1/2. And then the integral from 0 to 7. The area above and the area below from 6 to 7 are, we can call those a zero pair if we want, just like when we add integers. Those cancel each other out. The integral from 6 to 7 would be 0. So the integral from 0 to 5 is the integral from 0 to 6 is the same as the integral from 0 to 7, because when you go from 6 to 7, the same amount of snow fell as the amount of snow that melted. Okay. So anyway, we have 3 plus 1/4 minus 1/4, so we get a total of 3. And so I should indicate that right there. It's the 3 plus 1/4, and then we have to subtract the area below the curve. And then finally we have that 3 inches, total inches, that have fallen, or that have accumulated, I should say, and then between 0 and 7. And then finally, when x is equal to 8, the integral from 0 to 8 would be 3 minus the 1, or 2. Okay? An interpretation of what those numbers mean is a very important thing as well. So let's just take the 2. So in the first 8 hours, once we started this tracking of the snowfall, so in those 8 hours between t equals 0 and t equals 8, or x equals 0 and x equals 8, call it what you want, in the first 8 hours, what is the change in the snow level? Well, you should be able to answer that. And pause the video if you want to think about that, but I want to tell you the answer so you know what that is. The rate of change of the snow level is that there's 2 inches more snow, or the snow level is 2 inches higher at the 8-hour mark than it was at the 0-hour mark. So in 8 hours, a total of 2 inches of snow. I'm not saying that very well. There's 2 inches of snow more than there was at the 0 hour. Okay. So then part B. Let's see, we're at the 9-minute mark. Part B, it says f prime is equal to the derivative of, we already know that, f prime is the derivative. So then, if we take the derivative of an integral, what would you expect to happen? Okay, well the derivative cancels. They cancel out. They cancel out. In other words, it's kind of like this. This is the f of t here, the integrand, and the integrand gets, I don't know, this can't do it justice here in this video, but the integrand has something being applied to it, similar to when you multiply. Multiply a number, then you divide by it, it cancels it, those cancel out, and what's left is what you see there. So f of t being the integrand, when it gets surrounded by the integral symbol in this dt, the only thing to undo that would be the d dx. If you d dx it, it undoes everything, and everything falls apart, falls away from the f of t, and you end up getting f of x. Okay, so the integral with 0 to x dt, that all goes away when you take the derivative of it. The derivative of the integral is the integrand. Okay? So now this is the cool part, that you can fill out this chart, and now if you notice here, this is an f prime. Okay, so I want to make sure that's clear. This is f prime of x, capital F prime. And so capital F prime of x, when x is 0, is lowercase f of 0, and that's 1. If you look at the graph, that's lowercase f of 0. So all you have to do is look at the graph for this one. You don't have to accumulate area. F prime is not accumulating area. F prime is only lowercase f of whatever. F of 1, capital F prime of 1 is lowercase f of 1. And lowercase f of 1 is 3. Lowercase f of 2, then, is equal to also 3. Capital F prime of 3 would be lowercase f of 3, which is 0. And then the rest of this, negative 4, 0, lowercase f of 6 is 1, lowercase f of 6.5 is 0, lowercase f of 7 is negative 1, and lowercase f of 8 is negative 1. So dot 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 on all these guys, so that's kind of a neat thing. Okay, you're going to be asked these kinds of questions a ton, so if what we just didn't really make a lot of sense, then rewind the video and play it again. Okay? Now, let's go ahead and finish this up. On what subintervals of 0, 8 is f, capital F, increasing? So in other words, when you look at the graph, when are we accumulating snow? Well, we're accumulating snow whenever the graph of lowercase f is above the x-axis. Okay? So on the interval from 0 to 3, and also we accumulate snow from 5 to 6.5. Now I'm not trying to take this lightly. I'm not trying to make light of this, I should say, because this is not easy to see. So it's increasing. It meaning the snow level is increasing on these intervals. F, capital F, represents the snow level. The level at which the snow is, not the rate, but the level. How much snow has accumulated in that amount of time. Okay? Either the snow is falling, or the snow is melting, or there's more snow. The height of the snow is either going up, or the height of the snow is going down. Well, capital F basically is showing us what the height of the snow is. And the height of the snow is getting bigger on these intervals, and it's decreasing on the interval when the graph of lowercase f is below the x-axis, and that's from 3 to 5, and also from 6.5 all the way to 8. Okay? Where in this interval does capital F achieve its minimum and maximum values? Well, I think what would be better is if I waited until the next video to talk about D. Where's E? There's no E. Alright, so D, F, and H. There's no G either. How about that? Am I missing something? I don't know. So in the next video we'll talk about this part of it, and then because there's a lot to this next part, and I'll see you then.